Good evening, all. We will start the session at 6:05. Okay. Okay. In the meantime, anybody wants to say something about how was your quiz two and all? How did you feel it? Your response? It was good, bad, easy, difficult.
Sir,
What?
good, excellent.
Okay.
Sir, could you repeat again, because your voice is little bit echoing for me.
Okay. Wait. Just a second. Is it still echoing?
No, sir. No, sir. Now clear.
Okay, okay. Yeah, I was saying that any pointers that you all have, any suggestions, or how did you feel the quiz? Was it difficult? Was it easy? Yeah, something like that.
Yeah, sir. Actually, the quiz was really nice, but I'm confusing in last two questions because they are asking, they're given some dictionary and the first two variable initialized with that dictionary. So that is on the two variables, they are initialized with the function calling, procedure calling. So on that function, that given dictionary is play a main role. So I think what I think, if we call that function, then the dictionary will be updated.
Correct, correct. Yeah.
Yeah, but I can't get it what the mistake is.
The point here is dictionary has paused by reference in procedures. So if you consider that, then that will work.
Sir, actually, if the dictionaries play a main role in that procedure. So after completing that procedure, the side effect is affected that dictionary. So the first variable, the completion of first variable, I think there is something computational or whatever maybe the word is given. So that word count or whatever maybe that is in the dictionary. Then after again. Another same, they are using the same dictionary. I think the modified dictionary will be the part of that one, but But I have a little bit confusion, sir, because I need.
Yeah, it would be if we are returning, right? If we are returning and storing it into the dictionary, as you said, so it would be modified, and then we are using that in the next part of the code most probably. I don't remember the question exactly, but something like that was there, is what I suppose. So yeah, it could be changed, and on that you would work again on the next part of the code.
Okay, sir. Okay, then I think correct. I think
Yeah. Okay. So actually today's class we will discuss very new two topics, right? One algorithm. One thing is, first of all, what is algorithm? I use the term algorithm, but I would explain what it is, because we have not. Yeah. Is my voice okay, or is it still
step
echoing?
by step instructions.
Acha, okay, you are saying about algorithm. Yeah, I would come to that. So I'm just trying to give a summary of what this session would be. So in week 11, we would, as you have seen that most of you about the lectures, that how we actually use the graphs, right? We have been using the graphs till now. Now we would learn something new on the graphs, some useful technique to draw some proper insights from the graph, right? We would do that. And that technique falls under a broad variety of what should I say? Again, I would use the term algorithm, but I would come to what it means. So, a broad variety of techniques. If I kind of say, do not say algorithm, I would say techniques. Yeah, so this falls under a broad variety of techniques, which we call graph traversal techniques. Okay, or more appropriately, graph traversal algorithms. So what does that mean? That when you have a graph, I mean, this up to 10th week, we have seen the notions of graph, how directed and undirected graph can be represented in computational way, right? And then we learned a little bit of operations on the graphs as well. We learned about adjacency matrix and how we can work upon them to apply some conditions and all of that. But now we would learn that once you have the graph, right? In week 11, we would learn once you have it, then how can you traverse through the graph? How can you travel through the graph? Traverse means how can you move through the graph and draw and fetch some useful insights from it. And fetching some useful insight, we would not do that much, at least in this course. We would do a little bit of it, like we would see that given a graph, right? I discussed in the introduction to graph live session that a graph can be disconnected as well, right? A graph can be consisting of multiple separate components. A graph is basically a set of vertices and edges. Now, this set of vertices and edges can be disconnected as well. Let's say there are total 8 vertices in a graph, and 4 of them are connected together. The leftover 4 are connected as separately in a different. I mean, the other 4 are connected, but those 4 are separately connected. The second half, the last 4 nodes are not connected with the first 4 nodes with any edge, right? So basically, there are 2 bodies. Now these 2 bodies are separate disconnected bodies, and the whole thing we say one graph, and these 2 are disconnected components of a graph, right? And so these are basically components. The exact term is components. So graph can have multiple components as well, which might be disconnected. Now we would see that given a graph, which you do not know about the structure of the graph, right? Just a graph is given to you. Right now, visually you can see it as a human being, but computer cannot see it visually, right? They would just get the data of the vertex and the edges. Now, once you get that data, how you can run some program on the computer on that graph, so that we can understand that all the nodes given in the graph are reachable from any one of the node from where you are starting. Okay, and if it is not reachable, then you say it's not reachable. So this is what basically the fundamental idea of graph traversal is. Given a graph, you start from a node and you try to travel to all other nodes by using the edges, right? And let's say some vertices or nodes you could not actually reach, then you can say from my starting node, these are the nodes I could not reach. So there does not exist a path between these nodes, right? Something like that. So that's what we call the reachability problem in graphs, and that's a very fundamental notion of working with graphs. So we would actually discuss that part, and we would discuss some how do we travel, right? I told you that we would use some techniques to traverse the graph. So what is this technique, right? And there are multiple techniques, but in this course we would learn only one. And I would briefly give you an introduction to another counterpart to it, right? So I would discuss that a little bit. Not algorithm, but not the code or pseudocode or any thing, but the basic idea of the other algorithm that exists, very prominent one. So we would discuss these things. The gist is that once you have a graph, you want to check some useful, you want to fetch some useful insights from the graph. Then you have multiple techniques to do that, multiple programs that you can run. One of them is depth first search, and that graph traversal technique or graph traveling technique of depth first search we would discuss. But before going to depth first search, we would actually discuss another important new notion in programming, that is called recursion, recursive function. So what does that mean is we would discuss that. This is a specific kind of function, right? You all have a function or procedure, whatever you want to call it. So we have not yet seen these kind of procedures, right? What we have seen, so what was procedure doing till now? Procedure was either modifying some variable or modifying some table or array or dictionary. It was changing something, or let's say reading from something and producing an output, or some kind of manipulation on the data it was doing, right? That's what procedures task was. And after manipulating the data, it was not doing anything else. Later we learned that a procedure can also return, right? We have seen a few examples here and there that and even if some of you are not aware of, then I'm just telling that. So a procedure can also return value, right? Because you have seen, right, when if we call a function and a procedure or function, same thing, and then you work upon some variables and then you return that variable. So procedure returns that variable after working upon it. Okay, so and then you can store that variable, store the returned value into another variable, and then you can use that variable to do some other task. So that is the second property of procedure, that it can return values after operating. Now the third thing that we would now discuss is recursion, and that is a procedure can also call itself. Now what does that mean? We will discuss. Okay. Yeah. So any basic introductory kind of doubt, or I have not started the session yet, but just any questions you can ask. I will start.
No, sir. We will start.
Fine. Okay, so I would at first discuss the recursion, and I would be discussing a little bit extra topics on the recursion, which might be very, very new to many of you. Those who are from CS background, they would feel it, that they know all of that. But for those who are not, it's very important. But this is not as a part of the syllabus of this course. Neither will it be important for your examination. At least not the whole thing. Okay. I mean, understand whatever I would try to discuss, but I would tell you that these parts are not essential for your exam. So those parts, even if you don't understand, that is good, that is okay. But if you, if you understand those parts, then it would help you in your future courses, right? Because those things we would not discuss in any of the courses after that, and then kind of you would jump in your diploma level courses directly on those concepts. So you would feel difficulty over there. So like in PDSA course, like in DBMS, Java, all those courses would require that concept. So I would discuss that point of view of recursion as well, which is not important from the course perspective. I mean, CT course is computational thinking perspective, right? But try to understand and ask your doubt wherever you have. Fine. So let's start with recursion. Now, what is recursion? Simple definition is a function, or I would use the term function and procedure.
Yes.
In one place or other, they are kind of same thing. There is a subtle difference, but those kind of difference does not matter. I mean, at least in our courses.
A function called by itself.
Yeah. So a recursion is nothing, a function calling itself, right? It can call itself, right? So calls itself. That's the definition of recursion, right? So if I, let's say, have a function, right, or a procedure, let me use the procedure name here only. So if I have a, let's say, procedure, right, whatever ABC, okay, and let's say this is the procedure starts, and let's say I'm just writing a normal thing, and then you do some task over here, okay, and then again you call the procedure. I'm sorry, not procedure, ABC. Right. And most probably you would have some arguments over here that would. So this is called, so inside the body of ABC itself, we are calling ABC again. How does it make sense and all? We would discuss some examples and it would be fine. But before that, recursion means this much only. You are calling a function inside the body of the function itself, right? The same function. Now, the thing is how this actually operates or how this actually happens. Okay. See, let me just tell one or few more things. So let's say this is line 1, this is line 2, this is line 3. Okay. 4. Then let's say there is another function called procedure called, let's say DEF. Okay. And let's say now this is the body of DEF, and inside DEF you do line 5. Fine, something like this. We have two procedures, ABC and DEF, and suppose this is the way we are calling the functions within each other's body. Okay. Now my question is, let us actually try to go through how the order of execution would turn out. Right. So let's say initially you are calling ABC. Right? ABC is the first function to be called. So can you help me with the order? How I mean first line 1 would be executed, right? No problem. So line 1 to line 3 would be executed as it is because they are in the order. After that, what would happen?
The recursive part is calling, sir.
Okay, so what would happen?
Sir, actually I have a doubt because if it is a multi-thread language, then after the
just consider single thread. There is no multi-threading. We have not, let alone threading. Simple. This normal program you are running in one instance, only one. I mean, since you asked, there is only one thread and everything is normal. Yeah. So in that perspective, you say.
Okay, sir. Sir, this is my guess only, but I don't know what is the exact workflow. So I think after completing the recursive part, the line 4 is executed, or line 4, line 5.
Okay. So ABC, what I mean is, so let's say I would actually put here like this, right? ABC iteration 1, ABC 1. So this one at the top means the first ABC call, right? So this, when I call the ABC on my own for the first time, that is my this call ABC 1, right? So if the second time ABC is called, then I would denote it with ABC 2. So let's say line 2 of second call of ABC, I would denote it something like this. So now you can tell what would be the second step. Okay, so if I just write it, so it should be again line 1, 2, 3 of ABC 2. Why ABC 2? This is your ABC 2. This is the second time you are calling ABC. I mean, second time you are calling ABC. So this is the, and initially you called ABC for the first time, right? So this call was ABC 1. So line 1 to 3 was executed as a part of first ABC call. Then we are executing, then we are getting to this line which actually calls ABC itself. That's what we call recursion. And since there is a second call to ABC, right? So that's why I wrote here on top 2. So again, the point to observe over here is, for those who are new to this, that we do not execute line 4. Okay. Once we get this ABC call, right, we do not execute line 4 and later execute ABC 4. No. Whenever you get a call to any function, you directly jump to that function. Okay. So directly go to that function wherever it is and try to execute it. So from as soon as I get this ABC call over here, my program actually jumps to the ABC procedure over here, I mean from the start, right? Now, but this is the second call to ABC. So again, line 1, line 2, line 3 would be executed corresponding to the second call of ABC, like corresponding to this call, I mean. Okay.
Yes,
that's
sir.
why I wrote, yeah, line 1, 2, 3, ABCD.
Excuse me, sir.
Yeah,
But sir, I can see this as a loop. Like I feel like
correct.
first ABC 1 will execute like one, line 2, line 3, and then it will switch to ABC 2, and then again line 1, line 2, line 3. But how this loop will finish? Because I
Exactly.
feel
When this reach the base case, it will return something to A, B, C, N. So
there should be some exit to come. I mean, there
Exactly.
should be something to come out of that loop, right?
yes,
Exactly. That's the whole point I was trying to actually. Thanks for bringing that up. That's the idea that I was trying to bring up. So since I have written this ABC, see what would be the third iteration. If I go for one more step, so then again ABC would be called in the ABC2's body, right? Now I am ABC2's inside ABC2's body. So line 1, 2, 3 got executed inside ABC2's body. So these three are done inside ABC2's body. But again, I would see again ABC. So this would make an ABC call ABC3. Okay. So again, we would go to the top and again start executing like from line 1 to same thing, right? Line 1 to 3, but this time corresponding to ABC3. Now, so this goes on and on and on. It would never stop unless and until you have a condition that's one of you rightly put that this is what we call the base condition.
base case. Yeah.
Okay, so base condition where the recursion stops. I mean, so a recursive code, a general recursive code, recursive procedure, it should look something like this. Okay, the body starts, let's say the function is like this, the body starts from here. Okay, and here initially you would have one base case. Base case. Now, what this base case is, it is nothing but one kind of if. It can be mostly it's if condition. So you would have one if condition, and if that condition satisfies, then you would return some constant or some variable, something like that, right? Something. So you would return some value. Okay, you would not call another value. So this is base case. You would understand what do I mean by call another, not value, call the same procedure. The second is the just a second. The second is the recursive case. Recursive case, or we also call it inductive case, whatever you want to say. Inductive case. So in this case, what happens is we would actually return. We can do some operation over here before returning. Some operations can be there, right? You might do some operations, but followed by this operation, the thing that we must have is return this function call, our general whatever this recursive procedure. I'm writing in short, recursive procedure (GRP) with some arguments. So let's say there are also some arguments. So this is the basic body of your recursive procedure. As you can see that this line would go on making the loop as you were saying, right? Like this ABC over here, right? But the thing is, when this base case is reached, right, and this base if condition would be depending upon these parameters that you are saying, right? These parameters. So let's say whatever operations over here on the parameters you do, that would actually change those parameters. And in the base case, when you actually reach that value of that parameter, right, then this if condition would get satisfied and you would return some value. The thing is, here you are returning a value and here you are calling the function. Calling the function means it's not terminating, it's again calling another one, and in turn that would go on. But as soon as you return a value in the base case, right, that means it's terminating the function. It's moving out. So the function got finished, right? No, it's not calling another child function. It's getting terminated over here. It's returning the value. Okay, so this is the general body of a normal recursive code. Once we go to some examples, it would make more sense. Yeah, you are asking some question. Go ahead.
No, sir, I wasn't asking. Now it's clear. Thank you.
Okay.
Sir, I have some questions.
Yeah.
Yes, sir. In a procedure, if there is no base case, then what's happening?
If there is no base case and you do not have any other break condition or some
Execution.
specific, right, some exit condition, then it would go on and on and on. And I would also discuss something like that interesting fact about
Infinite. Yeah, sir. It's go
Right.
to infinite loop, but
yeah.
when it is end,
When
what is my question is, sir, if there is a running time for if I run the
Yeah.
code in Python, so the Python creators are fixing some time for the function execution. So it's go
Yeah.
to infinite loop, then after some stage it will throw exception or error like
Correct. Buffer overflow. Right. I would discuss that. That's what I was saying, that you would get an error or an exception that it's not actually related to time. It can be mapped to time, but it is more related to space. Now, this is the topic that I was telling you that I would discuss, and these things are not there in the course, and you would not see these things in any further courses until you actually reach at a level that you have to implement these things, right, in the diploma level courses. So that's why I have planned to discuss all those things, how recursion internally works in the system. Now, I know that you all are not, I mean, you don't have any idea about, I mean, at least from our courses, that how the system actually works. When you run a program, what is a program also we have not discussed. But anyways, I would discuss those things after I discuss the basic concept of recursion. Okay?
Okay,
From
sir.
scratch.
In if condition, the base case if condition, if I call
Yeah.
it another function,
Yeah.
so that is possible.
Yeah,
Like,
you can call.
Yeah, sir. If this here, if condition inside, I will call the function def, then def is invoked, then again ABC is invoked, then again def is invoked. It's
Yeah, exactly. And that then your base case of general recursive procedure function would depend on the base case of DEF function whenever it returns. Because your base case can only arrive when that function's base case gives the result, and that would be used as a base case condition check for your function. I mean, this general recursive procedure. So there are functions of that kind as well. In fact, I would again discuss one specific kind of function. You can check that out. Not discuss, I would just tell all of you. If you're interested, you can look at it.
okay. Sir.
Okay.
Yeah, sir.
Fine. Great. So yeah, so let's come back to the basic discussion which we are having. So this is the body of how a general recursive procedure would look. You would have a base case that would work as the terminating condition, and you would have a recursive or iterative case that would call the function itself by changing the parameters. These parameters, right? Some changing the parameter. It's not necessary that you change the parameter, but I mean, when you are using recursion, most of the times it is because you are changing the parameters every time, and with the new parameters, you want to do the same task which you did on the earlier parameter, but the parameter must be changed, right? So that's why that is a general perspective of using recursive codes. So that's why I'm saying that most of the time you would be passing some parameters, and then that would be again going through the same process, this whole body, right? So fine. So this is your terminating condition of your recursion, and this is your repetition or recursive condition, where you return a function call, the same function's call, and here you return some constant or some value, something which terminates, right? When you are returning from the function, you are moving out of the function or procedure. So that's it. Now let us come to the this sequence of operation as well. Now assume that now we know the base case condition, right? There should be some base case condition which terminates the procedure call. So like accordingly, ABC also would have some base case, right? Some base case would be there for ABC, and I have not mentioned. So these base case would be, let's say, something over here, or along this line 1, 2, some base case would be there, right? So that base case would be executed, and let's say in the third call of ABC, the base case actually gets executed, right? In the third call of ABC. So this if condition for ABC gets satisfied in the third call of ABC. Assume. So in third call of ABC, actually what would happen in that case is, I would return back. I mean, third call of ABC would return back. Where it would return? It would return to the position over here. I mean, where it was being called. ABC3 was called over here, right? At this line. So it would come to just immediately the next line. Okay.
Yes.
So now the next thing is my line 4 would be executed. Fine. Actually, one small mistake I did. See, if in the third call of ABC my condition is terminating, right? So don't confuse this ABC3 with the inside the body of the third call, right? So maybe line 1, 2, and 3 would be executed, but then it would return. The third ABC call, I mean, would not happen, right? Because that's the base case. So what I mean is, let's say in the third ABC call, this happened. I mean, your base case is executing. So let's assume that line 1 and 2 was your base case. Okay, so only line 1 and 2 would be executed here because that's your return condition, something like this. Okay, so that thing is there. And anyway, so after that, when we move out, we would reach at line 3, right? So now I come to line 4, but the important point is, when I am at this line 4, which ABC phase is going on? Is it ABC phase 1 or is it ABC phase 2? I mean, line 4 for which ABC? Line 4 is there inside the ABC procedure, right? But you see that we have called ABC 1, then again ABC 2, second time it was called. So when I return from the third ABC call, after executing the, let's say, first 2 lines, assuming these are the base case, okay. So when I return from the third call of ABC, to which version of ABC call I would return? So this line 4, when I'm returning, to which version of ABC? Is it ABC 1 or ABC 2?
So 2.
ABC 3
Correct.
is written to ABC 2.
2.
Exactly. So we would actually always go back in the same order as we moved in. Okay. So you have to go back in the same order. So 1, 2. So if you moved in this order inside the recursive call, you also have to move out in the same. I mean, in the just the opposite order in the same. In the same order in the opposite direction. Okay. Anyways, fine. So now line 4 for ABC 2 would be executed. Okay. Do not confuse this with ABC 1. Fine. So line 4 is done. Then what would happen? Then I see that DEF function is called. So again, this everything, whatever happening is here is under the body of ABC 2 call, not under ABC 1 call. So this DEF call would happen under again for ABC 2's body, the second instance call, right? So DEF function would be called. Now inside DEF I go, line 5 would be the next thing. So line 5. See again, line 8 I did not execute. Whenever a function is called, I would directly go to that function. So again, line 5 would be the next thing to be executed, and then again I am executing ABC function over here, right? So what would happen? Again, call of ABC. Now this would be my actually this would be my fourth call to ABC, but since here I have not mentioned that because ABC 2 was the last successful call and ABC 3 was the terminating call. That's why I never wrote ABC 3, but ABC 3 was the third call of ABC. So third call, I'm writing third call of ABC. ABC, okay, but it was terminating. But here the fourth, this is the fourth call of ABC. Fourth call of ABC, but I'm writing ABC 3 because this is the next successful call, fourth call. Okay. So now ABC, this line would be executed, and I would again go over here. So ABC corresponding to 3, line 1, 2, 3 would be executed. Right, 1, 2, 3, 1 by 1, and suppose again it terminates after 1 or 2 instances, right? Again it would again go to this line, and again the recursion would happen, right? So again maybe you may go to ABC 4, right? ABC 4, which is the fifth call, right? And again whatever, let's say fourth call, this one was your terminating condition. So line 1 and line 2, the base cases would be executed, and then I would return that. Okay. So where I would return again at line 4. So now again at line 4, but again, what is this line 4 for? I mean, for which version? For ABC 3, because 4th was getting returned. So ABC 3 would be the one. And this ABC 3 is under which functions call? It was under the function call of DEF. Right? I mean, actually ABC, another ABC is there, right? So ABC, and then you have finally you have the scope of DEF. So I made this thing complex. I thought to make it complex because just understand the complexity that can go up when you call functions in this chained manner inside one body of another and like that. So, but what you have to understand is, whenever you get a function call, you directly go inside the body. Okay, keep track of the version of the call you are doing when you are doing recursion. So this track of version means these versions I'm talking about. When you return from a particular function call, right? So here you return in line 4. Here you return from which one? From the third call of ABC. So in which version of ABC you would return? What is the value of the variable? Very important point. What is the value of the variables in this version? What is the value of variables in the version of ABC where you return? Okay, if you mistakenly consider that this return statement, right? This line 4 is corresponding to ABC 1, then you would mess up with your answers. Okay, so just be very careful which version you are actually going into. Fine. So on and so on, this would go on. I mean, I'm not discussing the whole step every time, but this is how it would happen. And then once you return back to DEF, right? So again, this line 7 would be executed, and this whole DEF function would terminate after that. So after that, line 8 would be executed because you come back over here. Once DEF terminates, you come here, right? And then DEF is done. So line 8 would be the next one to be executed. Line 8 gets executed, and your whole, this whole thing terminates. Right. So this is how the basic things work.
Sir, after
Yeah.
line it executed, ABC2 is end, then that is must return something to ABC1, then ABC1 is
Returning is not compulsory in recursive call, but mostly it is the case of return. So I have not written here any variable n equal to something or something like that, but I've just called the function just to discuss this program flow. But returning is not compulsory in function. So let's say if I write something as, what I mean is, let's say the base case, right? So you have the base case, some if condition is there, you're doing some work, and let's say you're not returning something. If something happens, you're printing, let's say you're printing something. Okay, now again, the notion of print we have not discussed in CT, but assume that you are just printing something on your screen, right? Just that you print something, and else you do the, I mean, you call your function, whatever.
Yeah.
So anyways, so that's it. Regarding the this recursion call. Now I would go how recursion works. Right? When you are calling one function, this is not regarding recursion. This is how actually any function call or any procedure call works. Right? Now we have not discussed all those things here, but let's not do that.
Sir, you're telling like after the line 8 execution, the whole recursive part is end.
Yeah. Once you end up over here, then it's not a loop, right? Unless and until I get another function call, it would not end. But yeah, one important point is line. See, this I called ABC 2 times, right? ABC1, ABC2.
Yes.
So this line 8 would be for ABC2. I mean, the first time I'm moving out from DEF, that would be for ABC2's
ABC2.
moving out. Yeah. So again, where would I land up? This. So from here, I would return over here, right? So what was here? Up to 3, and then ABC1 was calling the second instance of ABC2. So that would be corresponding to this line. So again, for ABC1, I would execute line 2. So after line 8 gets executed, right? Some point your line 8 would be executed, and that would be for ABC2's version. And after that, the next thing that I would do is line 4 would be executed for ABC1's version. The first version, I mean.
Yes.
Line. And then again DEF would be executed for ABC1. Then again you go inside ABC, this DEF method, call execute line 5, execute again ABC. Like that you would end up at some time at line 7, and then you come back over here corresponding to the version of ABC1, and then at some point at the end you would execute line 8 corresponding to ABC1, and that's your end of program.
Yes, sir. So if I write their written statement after line 8 or not, so that is not a problem. So after in our problem, ABC2, the line 8 executed, then after ABC1 is executed or not, sir. So that's a little bit of doubt.
ABC2, sorry, can you repeat?
In our program, ABC2 line 8 is executed.
Yeah.
So after that execution, ABC1 is going or it's end.
Exactly. See, ABC2's line 8 means what? ABC2 is terminating, right? Everything related to ABC2 is done. That's the last line, correct?
Yes,
now you have to see if ABC2 is terminating, then where would the control go? The control of your program would return to the point where ABC2 was called, because that's when you jumped inside ABC2.
Yes, sir.
Right?
ABC1.
Yeah, so it would jump to that point or to that line where ABC2 was called for the first time. We know that ABC2 was called here for the first time.
Yes, sir.
Right? So, and inside which body is ABC2 called? Inside the body of ABC1, because here you have ABC, right?
Yes, sir.
ABC1's body. So therefore, you would return over here. At this point, you would return. After your ABC2's line 8 is executed, it's finished, and since it is finished, it would return to the point where it is called. So it is called over here, so it would return over here to the next line, which
Yes,
is
sir.
line 4.
Yes, sir. Now
Right.
clear. Yeah.
And that's why I wrote at once you execute line 8 of ABC2, after that you would execute line 4 of ABC1. So because your control returns
Yes,
inside the
sir.
body of ABC1. Fine.
Yeah.
Yeah. Fine. So this is how the general flow of recursion works. One very important point that I am telling is with respect to your exam questions. So recursions, most of the time we do mistakes in keeping track of the version of the function where we are returning. Because in every version, in ABC1, ABC2, here it was just an example, but when you really see the codes, each of these versions would have different values of variables, like in X or whatever the variables are used, they would have different values, right? So when you return from a function, from a recursive function, just keep track of to which version of that function you are returning from the recursion. If you miss that, then you would actually end up having wrong values of the variable. Wrong means the values which are not pertinent to that iteration, or sorry, that recursive call of the function. It may be the previous recursive call of the function, and you would end up with wrong result. Okay, so just keep that in mind, be careful with that.
Yes.
Now, yeah. Now I would discuss, now this part is not necessary to your understanding for your CT course or any course as of now, but it would be very much essential for your diploma level courses. So the thing is, we have till now discussed about the idea of computation, how we do computation, right? And maybe we have learned a little bit of programming ideas, right? We have not gone into any particular languages, but we have learned how to actually convert our way of thinking a problem into the way that computer works. So that we have by using pseudocode and codes, right? So now we would discuss, yeah, that a little bit of actual systems thing, that how when you write a program, right? So this is a pseudocode, and when you the next thing you would learn is Python. So Python would not be that much different from this pseudocode which you are studying. It would be different, but you would be able to cope up with it very fast. So basically, you can assume that whatever pseudocode you are writing now, that is kind of a program. Just assume that. Okay, now when you run that program on your computer, okay, so what actually happens? So when you run that program on your computer, and if I say specifically in terms of function, a lot of things happen, but I would address only with respect to these function calls or the procedure calls, right? And then I would go to the recursion aspect of it. So when you actually run a program in any language, it may be, when you run it on your computer, right? And there is a function call, right? So let's say there is a function called A, right? And here we have the, let's say, procedure A inside the program. Some task it is doing over here, and here it is ending. Okay. Now the thing is, let's say within this some task, again I would take one example where I'm calling procedure B. Procedure B is also here, some task it is doing. Now how this happens? See, initially I called A only. A in turn called procedure B. Okay. So how this is implemented inside the system is a separate space inside your computer's memory would be reserved. Now this space has many properties. I would not go into the properties of this space and what is this called actually, but a space would be reserved, and inside that space what would happen is whenever a function call would happen in your program, whenever, right, a entry in that space corresponding to that function call would be inserted. Now what do I mean by entry? So in order to run a program, in order to, when you are calling the program, when you are calling a function, in order to run that function, some informations need to be preserved by the system internally. We did not worry about what information, but some information is required. Okay, so and that depends on every function call. So whenever I'm calling the first function A over here, some information, some bookkeeping task has to be done by the system in order to execute this function. Okay, so that information and that record that A function is being called is put inside this memory, right? Some metadata. It's kind of a metadata corresponding to the call of function A. Okay, then what happens? Your line 1, line 2 gets executed as usual, and then function B is called. whenever I said that whenever a function is called, it would be happening. So again, since the function B is the next one, I would put as the next entry corresponding to function B. Okay, inside the system. These are all just some bookkeeping information, right? Inside a separate space in your memory, computer memory. So B's information is kept and then B is executed. Now the thing is, if B would have some base condition, I mean, even if it's a normal function, it would have some return condition at least. If it's recursive, then it would have some base condition as well, but it would have some returning or some terminating condition, right? Even if it does not return, it would have one termination, that when it ends. So that point when B returns or ends, that is B moves out at this point, right? Actually not this point, at the next line over here. Before that, right? When B moves out over here after completing its whole body, so that time B is now out of the context. B has now been completed, right? It has completed its execution. So that's why what would happen is this entry which was there corresponding to B would be removed, right? But A is still there because A has not completed its work, right? So A is executing this line as of now. So once this line gets completed and A reaches its ends, then A would also be moved out of this system. So once the function moves out of its execution, completes its execution, right, it would be moved, the record corresponding to the metadata corresponding to that function preserved in a separate space inside memory would also be moved out. And whenever a function is called, a record corresponding to the metadata of that system, function would be inserted into the memory inside the system. Okay, so a separate memory space keeps track of whenever a function is called, it inserts the record whenever the function call happens, and it removes the record whenever the function completes its execution, right? And let me just mention, some of you are interested, this is what we call a system stack or call stack. Okay, now what is stack and all, you need not worry about that, just I mentioned it. And these records that I was telling, that is metadata information or whatever, right? These records is what we call activation records. Okay, and this whole memory thing is present inside your RAM, right? Inside your primary memory, your random access memory. This whole thing is present inside your RAM. Okay, and some part of it in some optimization can be converted and can be taken up to the cache memory as well. Okay, some cache as well, but that's not always happening. But it generally is always inside your RAM. Don't get over, those of you are new, please, all these things are not required. Just understand this basic thing that whenever a function calls happen, there is some space, right? I don't need to worry about what is called. It's called system stack, what is stack, I don't need to worry about them. There is some space which keeps record of these functions whenever they are called and removes the record whenever they are completed. That's it. Now, the point that I discussed this is, as you questioned also, that if I do not have a base condition, what would happen? Now see,
Stack Overflow.
yeah, exactly. So this is the system stack I told you, and obviously since it is present inside your RAM is not that big as hard disk or something, right? It's 8 GB, 16 GB, maybe 32 GB, not more than that. Generally not more than that. So even 32 GB is very rare, is I would tell, in normal personal computers. A 16 GB is also good. 8 GB is quite common these days. So what I mean is, the RAM space is limited and there are a lot of things going on inside the RAM, right? Everything that you do on your computer happens in the RAM, right? So it is limited space. So I cannot provide you a huge amount of stack space, this space I mean, in the RAM. And since it is limited, it would have one boundary, obviously. Now, if you have a recursive call in a function, so this was a normal function call, right? There was no recursion. A was calling B method.
Yes, sir.
And that's why I had A and then B. But what happens if I do a recursion? So A is there and inside this A is again calling over here. Let's say this is my body of A, some task is done over here and some task is done over here. In the middle, A is being called. What would happen? So A1 would be the first one, then A2, and let's say no base condition.
Going.
Right? No base. You do not have any base condition. So A2 would be there, again corresponding to A3, one record would be inserted, dot dot, this would go on and on until it reaches this last level. So once it reaches this last level, obviously, because you are not terminating, right? Remember what happened in this case? In this case, we had A and B. A was at bottom, B was at top. But B got terminated, and that's why it was removed out. It was
Yes.
removed out of the system, right? But here we are not removing, we are just going on top. So that's why once it reaches this bottleneck level, then it would return you your programming language would return you that your the exception would be Stack Overflow error or Stack Overflow exception, or some programming language do not give the Stack Overflow, they tell you the time limit exceeded kind of error. But this is not actually related to time, this is more related towards the stack space. Not more, it's totally dependent on the stack space, right? So these record that you are maintaining, they are all the recursions so many times that even the record, the memory taken up by this record itself fills up that stack, and that's why your program terminates. It actually crashes. Okay, so this kind of error with recursion infinitely, or the main case is when base case is missing. So this gives rise to Stack Overflow error. Just as a trivia for
Yes.
those, this is not required for CT, but this is important. Just understand, you don't need to go into the specifics of all this, just understand a basic overview that this is how the system works. Okay.
Sir, if rather than recursion, if any possible to get the Stack Overflow error?
There are ways of doing that, but so see, there can be two possible ways of filling up this memory. First is you have many records, and the second is you have lesser number of records, but the record itself is of huge space. So if I have the same memory, but let's say the record itself takes this much space, so I can mostly take up to two records, right? Not more than that. It's not two practically, but there can be situations where you can end up the stack space by around 30 to 40 calls of the function. So that means your function needs to be that much heavy. It must use a huge amount of data. So whatever information that is maintained inside this activation record, they should be very much heavy. So then that would fill up your space. Okay, even without recursion, let's say in a loop you are calling the function maybe 10,000 times, and
Yes.
the function itself is quite large, then also you can end up the stack space.
Yes, sir, clear.
Yeah. Fine.
So why we are interested in recursion? Because we are using loop to easily understand the situation, and the flow of execution is also easy. But in recursion, it's take a lot of time and hard to understand. Maybe it's look pretty, it's very simple, but
Exactly. So I get your point. The thing is, you all have not yet done that kind of coding that you would do in algorithm PDSA course, your programming data structure and algorithm, where writing the code using loops would take you around 50-60 lines of code, and writing it using recursion would take you around 8 or 9 lines of code,
yes.
not more than that, right?
So
Recursion, writing code recursively, right, in the recursive manner, actually eliminates a lot of subtleties, a lot of smaller corner case that you have to take care of when you write code in using loops. Now, in order to get this flavor, that's why this is the last week. So this is where we are terminating. We are ending the whole course, right? So week 12 would be mostly on some tutorials and some procedure writing stuff. But conceptually, theoretically, this is our last week. So now you have to actually, the motivation over here is that what happens next. So that you would see in the further courses, that when you go to write code which are very complex, right? So then writing a recursive version is much more easier. It is much more, as you said, it is visually more easy. It is more easy to think about it when you are writing a code to solve the problem. It is much more easier if you apply the recursive way of thinking, and you can find solution much faster. In iterative version or using loops, the problem is corner cases. You would end up in a multiple corner cases where you have to take care of it separately. See, the beauty of recursion is you are doing recursion. So let's say A you're calling, and over here you're recursively calling A. Now obviously I told you some parameters you would pass. The beauty is whenever you're calling this A method, except the first call, all call to the main body of A method was actually because inside the previous A method's body, this was called, right, in the previous A method's body. So that means whatever necessity, whatever variables or whatever prerequisite values that you need inside a n plus 1th call I mean, inside the execution of a n plus 1th call, you would have those values computed inside the a nth call. That's the main conceptual beauty of recursion. A nth call would take care of most of the tasks that you need to do in order to solve the a nth plus 1 call. But when you do it using recursion, iteration, using for loops, you are not computing, I mean, you are not calling a version of yourself again. If you are not calling a version of yourself again, there can be corner cases which you could not, which you did not address in the previous iteration of the loop, right? So therefore, those kind of corner cases end up creating a mess, and I mean, the code becomes large.
Yes.
So that's why recursion is easy. Fine.
Yes, sir.
But from performance point of view, from system point of view, always we prefer to write iterative code. Okay, so yeah, so mostly the thing that we follow is we try to come up with a solution which is recursive, because that's easier to think. Now, once we come up with a solution, once we are sure that okay, this can be solved by this recursive code, then we try to convert that recursive code into iterative code. I mean, by using loops and all, so
Yes.
that it helps us to gain the performance as well. Okay.
Yes, sir.
Fine. So these things would be much clearer once you move to new courses. Most, I mean, specifically speaking, when you move to PDS, so you would see what I'm telling. So okay, so this is about recursion and in general function, how functions work inside the system. Any doubt in this discussion? Please go ahead and ask. Any basic doubt also, please, because this is a basic topic. Please ask. No doubts? Okay, great. Fine. So this was about recursion. Now we would see some codes about recursion. I think Sir has discussed that in the lectures. I would just kind of go through them. If you have any doubt in any specific part, you can tell. So now I told you that recursion would mainly, we would pass some arguments and then modify it. So let's say factorial is one code that is there. Right, I need to write a factorial method, right? So how can I write it? So something like that. I would have a procedure, let's say factorial, okay, and let's say I pass a value n, okay, n is the number for which I need to find factorial, okay, and let's say I have as of now a for loop, right? I have a for loop, okay, and I write, now we have not gone, you have seen the for each loop, right, and the while loop, but assume what we are doing over here is, let's say we start a variable and from I equal to 1 to n, okay, so a variable would just iterate from I equal to 1 to n, every time it would increase by 1, and then inside this, like in for each loop, you have seen that every time you execute the for each loop, next iteration actually goes automatically to the next value inside the dictionary or tuple or whatever list, right? Something like that. So every time you execute this for loop, our I would be incrementing by 1 every time, right? So
Yes.
for I equal to 1 to n, what we would do is, I would need to have one variable here to store the factorial. So I would just call it, let's say temp, right? And obviously I need to do multiplications. So my identity would
One.
be 0, it would be 1.
Yes.
Addition identity would be 0. So temp equal to 1, and I would do temp equal to temp into I. Right? So that's it. So after the for loop gets over, at the last I may return my temp. So this is my iterative version of factorial, right? Using loops. Now how the recursive version would look?
So if
Procedure.
n equal to 1, it's written 1 or 0, it's written 1.
Yeah, exactly. N equal to.
Sir, or we can do like n into n minus 1.
Yeah, that's what we would do, but we need to have the base case, right? This is your base case.
Yeah.
So written 1
Until
else the function is calling return factorial of n into factorial of n. Sorry, n into n minus 1, factorial of n minus 1. Sir, here the else part is needed, so we cut the else, that is also work.
Exactly, because once you return, it doesn't matter. You are anyway going home. So if you delete it, no problem.
Okay, sir.
Okay. But, I wrote it, that's why kind of in the flow I write. It doesn't matter. If you write else, that also is okay.
Yes, sir. Yes.
Fine. So this is how it works. Now, obviously, by comparing these two, you wouldn't see the benefit of recursion because anyway, both these codes are easy. When you get a 50-60 line of code and recursion breaks it down into 4, 5, 7, 8 lines maximum, then you see, okay, that's the difference. So those things you would see in further courses. But anyway, so the idea over here is this. So this is my what base case or your terminating case, right? And this is what my recursive or
Recursive
inductive,
case or
inductive, yeah, inductive
Inductive.
or recursive. Okay. Now, if I draw a tree kind of structure to show how the function call happens, so let's say my initial factorial was factorial 7. Oh, that 7 would be a bit large. Anyways, factorial, let's say 4. Okay, n was 4 initially. So what would happen is n equal to 0 or 1? No, nothing. So return n into factorial n minus 1. So
Yes.
this is what I will do. 4 into
factorial of 3. So that's 3 into factor of 2.
Yeah.
It's 2 calls 2 into factor of 1.
Now see, this is where our base case comes in.
Yeah, so 2 into factor of 1.
Oh, sorry.
That fact 1 is it's a base, it's written 1.
Yeah, so this would actually return 1.
Yes, sir.
Where? Over there. See, this is not, this fact 1 is not calling another fact. So this fact was calling this one. This is calling this one, but this one is not calling.
Sir, actually, fact 1 is written 1. So there is a manipulation in 2 times 1 is 2. So that's 2 is written to fact 2.
Oh, sorry, yeah. Oh, sorry, yeah, correct. But actually, fact 1 returns 1 over here.
Yes, sir.
Inside this multiplication, and then the whole thing actually gets returned 1.
Yes, sir. Yes, sir.
I made the arrow wrong. Yeah.
So, sir, in this case, we don't need to take even n is equal to 0 because it won't go further, right? We can simply keep.
Actually, yeah, you can write return 1.
Yeah.
So then n equal to 1, you return 1. So yeah, so this is your terminating condition or base condition, and everything else is the inductive condition. Basic fact. So this is how recursion works. Yeah, there is nothing more to it, but the most important part of it is keeping in mind the flow of recursion. So how that the first part of the discussion that I did, and the second is why recursion is bad in some situation. I mean, from the system's perspective, from the performance perspective, it might be bad. And I also gave you the example of when there is a mutual recursion. Mutual recursion means, so in our example, the first example, the ABC method was actually calling itself, and that is a basic recursion, right? Normal recursion. And again, it was calling DEF at some point, another method. And inside DEF method, I was calling ABC method. So this is basically, yeah, so the pair ABC and DEF pair, these two are mutual recursive pairs. And if you see the lecture where sir is discussing that,
yes, sir.
the last lecture, right, the fourth one, part 4, you would see that we are using the explore on train and explore on station as well, and one is calling the other. Again, the second one is in turn calling the first one.
Yes, sir.
Right? So similar kind of example. So yeah, so keep in mind about which version you are currently in when you return from a recursive call. I'm just saying it again and again because that's what would only matter when you write solutions to your questions in the exam. So yeah, that's it. And one more trivia kind of thing I would like to just mention. So as you are saying that in the if condition, if I put another function call, and that is again a recursive in the base condition, if base condition, if I put another function call and that function is itself a recursive function, then it can grow up. I mean, the base case itself. So first of all, function 1 is a recursive function. Now function 1 has a base case where it should have get terminated, but inside the condition itself, you are again calling a recursive function, or let's say function 2.
Yes,
so even the terminating condition of function 1 depends on another recursion, which is function 2, and that depends on the base case of function 2. So this is a huge chain of recursion, right? So just some trivia I would discuss now. First point is, most of the program, I would not say all programs, you would see somewhere or some places it would be told that all programs or all problems which are solvable using loops, which are solvable using iteration. Loops means iteration. Okay, they can also be converted into recursive solution and vice versa. This is true, right? The theorem, not theorem, I would say the statement is that all recursive problems or recursively solvable problems, solvable, just assume solvable, or recursively solvable problems can also be solvable
Iteratively.
and vice versa, iteratively, vice versa. But the thing is, although this is true practically, and in 99 I would say 99% of the cases, that's why I'm saying it's practically true, and you would assume that okay, if there is a recursive code, I can also write it in an iterative manner. But from theoretical computer science perspective, it's not actually totally correct, right? Because there is a specific type of problems which are which are not primitive recursive. So what are primitive recursive? All these things are not necessary. I'm just mentioning this again because it will be helpful in your further courses. So problems which can be solved iteratively and also can be solved recursively are what we call, basically these problems are what we call primitive recursive functions or primitive recursive problems. Okay. Now some problems are such that they are not, some recursive problems are such that they are not primitive recursive. That is, we cannot write loop versions of them. I mean, we cannot solve them using loops. Even if you try to write some modified, some very heavy version of them, it would not run, that's for sure. It would get into some corner case problem or some other complexity problem, it would not work properly, right? So these kind of functions or these kind of problems are what we call, they are non-primitive recursive problems. And if you are interested in one such problem, very famous one is, the first one in fact is Ackermann function. Okay. And so this is a function which grows exponentially. I don't know what to say. It grows super exponentially or hyper exponentially.
That means you are taking the order of growth of the iteration.
Yeah, so that means, as you said, that in the base case, let's say you are calling another recursive function. So that means what? For every function call of function 1, you have so many recursion of function 1 followed by so many recursion of function 2, right? For one function call of function 1, right? If function 2 is a recursive function in the base case. So Ackermann, so that is the growth. For a single function call, how many recursive branches you are making? Right?
Yes.
So that's what your growth means. Ackermann function is a hyper exponential growth function. So it creates a huge number of recursive functions for a single call to this. Okay, so that grows hyper exponentially, and there is something else what we call the inverse Ackermann. And obviously you can guess, if this grows hyper exponentially, this actually grows hyper slowly, or so to say, it decays hyper exponentially. Fine, just trivia, and not total trivia, because these things would be helpful in your upcoming courses. But what's important is the first discussion that we had. Okay, control flow of recursion. Yeah. Yes. So any doubt in recursion? If you are interested, you can check these things out.
Yeah, sir.
Yeah. Yeah. Go ahead if you have any doubt in recursion. Then I would move to DFS. Okay, great. Fine. So let me just tell one more thing. Suppose, anyways, that's not necessary. It's not going to all those things. So I would just go through the recursion slide once, see whether I missed anything or not. Factorial. Oh yeah, insertion. Sorry, it's one important part. The insertion sort discussion. Right. So this factorial and one list operation is discussed over there. How this is working, let's discuss that as well. So you know that recursion is basically what? The idea of approaching a problem using recursive solution is, you try to So this is inductive steps, right? We have seen that recursion works using inductive steps. So basically you repeat the steps again and again, and you change the size or the parameter list on which you are working. So here what you are trying to do is what, I mean, you have a list, right? And your inductive definition of list you have. Now what you would do is you would try to modify the list and make it smaller, and then every time you would call the list sum method recursively on the smaller part of the list. Okay, and then we would we have the first element of first L, which gives us the first element of the sub part of the list, and we would try to sum it up with the rest. So this is basically adding all the elements of a list using recursion. How we are doing it is, see. So first of all, think about the base case when it should terminate. So my idea is I have a list over here, right? And I have all the elements like that. My idea is at every recursive call, I would pick one element, right? And I would sum it up with the, assume that I have the sum of all this together, and I would sum it up with this sum. You assume that I have the sum of all of this together. How can I assume the sum of all of this together? The assumption is that okay, so let me just mention like this. Whenever you are trying to think of a recursive solution, right? The thinking process should be something like this. So recursive solution means it's a function, right? A recursive function. Recursive function. Fine. So if it is a recursive function, it would have some name. So this is your recursive function name, whatever it is. What you have to think while trying to approach a recursive solution is, what does this function, right? Recursive function, whatever this function is, what does it return? What does it return? You don't know how to return it. You don't have to think how to return it. That's the beauty of recursion, and that's why I was saying recursive codes are easy to think. So, but you don't know how it is doing it, or how it is actually doing that. But you have to think what does it return? I mean, what does it do? Once you are sure with that, then you can iterative or inductively mention the work. So what I mean is, so initially, let's say in this problem statement, you have to sum all the elements in the list, right? So when I write, let's say this procedural list sum, right? If I write list sum and then I pass the list inside this procedure, what does it return? That's my question. So the answer is summation of sum of all elements. Let's say all x element of L. Summation of all elements. This is what my list should return. So if that is the definition, can I write something like this? Okay, L minus, just assume that L, or not L minus, what should write it as? Let's say your init was there, right? So init, or you can init of L, right? So can I write it as sum of a list with, let's say it had n elements, right? With first n minus 1 elements. Can I say this?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
Great. So if I write something again like this, same list sum, and suppose by some syntax I have some, I'm halving the list. Okay, I'm halving the list. So just I write L by 2. This is not exact pseudocode, I'm just trying to make sense of it. So L by 2. So I can write sum of a list of size equal to n by 2. Since there are n elements, right? Sum of a list size equal to n by 2. Right? You can say that. So the point is, you did not know how this sum is happening, how list sum L was returning the result, but you just assume it is returning the result. If you just apply this chain of L minus 1, L by 2 is at some level you would reach L by 2, but every time you actually reduce the size of L by 1. How would you do that? By, let's say, init, right? You are taking the first n minus 1 element. Again, this recursive call, right? This recursive call would again call itself, and let's say this again it is calling itself with init of L. What would happen? Again it is calling itself by one lesser element, right? If this had 10 elements, this call would have 9 elements, and if this works recursively, right? Inside this body itself, if it is calling again itself, so next iteration would be with 8 elements, then would be 7 elements. So accordingly, it is getting reduced. So see what happens at every execution is you are getting one element separated out. And at each version of the recursive call, if you are able to separate out one element, all you have to do is sum that up at every recursive call. Like in factorial, what did we do? We did n into factorial of n minus 1. What was this n? N is that value corresponding to that particular version of the function, right? I mean, when you are calling n, because factorial n was the method, okay? And here we had the base case, and here we had return statement n into n minus factorial of n minus. So this n is the current value of the function call, right? The current version of the function call. So if I can separate this thing out, all I have to do over here was multiply, because factorial is multiply. And here you have to do addition, so what you have to do? Just have to add it. Just see this line, this is exactly analogous to your factorial. Only difference is over here. Okay, so one thing is we are summing up from first one or last, that depends whether you are using init or the rest, right? So I took the example using init, so my summation would happen from last element. Here the example is using rest, so we are taking the last n minus 1 element, and first one I am summing up every time, right? So this is directly analogous to your this statement over here, the factorial. This n is what? First of all, now here you are doing summation, so summation. Here you are doing multiplication, that's the multiplication. And obviously you need a smaller size value. That's why n minus 1. Same thing, smaller size value of the list. So rest of it, right? The next n minus 1, because first element I have taken over. So the next n minus 1 elements, and then you are calling the recursive then method. Here you are also calling the recursive. Exactly same, right? So at every version, if you can separate out the current value of the variable, you just need to do the summation. In this case, subtraction. In other case, where you have to do subtraction, multiplication, where you need it to be. So like that it happens. Okay, so you did not do anything else. What you did was you tried to figure out what it should return, and if I repeat the steps multiple times, then what should be my logic? That's it. And obviously, since we are doing this, I'm reducing the size of the list by using this rest function, rest operation. So at some point I must have a base condition, and that is this base condition. If your list is empty, then you return 0. Because summing up with 0 wouldn't matter anything. That's why plus 0. But in factorial we returned 1. Why? Because there it was multiplication. So if I return 0, so all of the collected value which I had would be multiplied with 0, and I get the 0 result in all situations. So since we are adding here, therefore our identity is 0, we are returning 0. Okay, so yeah, that's it. Any doubt in this?
No, sir.
Okay. Anyone else? Any doubt?
No, sir.
Sure. Now I will discuss the insertion sort, and then we can go to DFS. So insertion sort basics must be clear to all of you. So only difference over here is the recursive call, which is over here. See, we have a method over here which is actually doing the insertion sort. Putting the X element inside the list L at its proper position. Right? So I have this method. So there is no change in this method, it remains as it is. What we are doing is, what was our way of actually operating through insertion sort? So let's say I have an array of something like this, right? Array or list, whatever. Okay, and let's say this is the current, sorry, not one, let's say this is some iteration, right? In the middle I have some iteration, in the middle of some iteration. So I am considering this part, right? So what I would do is I would have this number, right? Then the very next number over here, I would consider this number, and where I should place it on the left hand side, where I should place it. That's my first, it's a one iteration. In the next iteration, what would happen? I would actually grow. Obviously, since I have now placed this red one over here, my array size would be, the left hand size subpart of the array would grow. Let's say it comes over here, right? And my red entry would be somewhere, let's say at its proper position over here, suppose, right? And now I'm trying to find the result for this entry, the new entry, let's say this one. Okay, this is my new entry. I need to find the correct position for this as well, and then place it over here in its correct position. So this is how I was moving with insertion sort. Now that means what? I'm moving the segment of the left part of the sorted array one by one. So every time it is a prefix, right? So let's say this was the n minus 1th iteration, this is the n minus 2th iteration, n minus 3th iteration, this is the first iteration, like so. Every time I'm going by prefix and trying to sort the prefix part. Okay, so if that is the case, that is actually a recursive thing that's happening, right? I'm just growing this part of the array, right? Like this. Every time I'm growing this part one by one, and like this, and then sorting. So this kind of a recursive step, because every time we are, let's say this one is a smaller part, this one is the larger part, like that we are going, which is actually contained. So this larger part contains all of the smaller parts. That's what happens in recursion. Recursion we call with the root, right? Some root. First time call would be there with some n, and then I would go with the two, I mean the tree structure, something, whatever the tree structure would go. So basically we can write insertion sort in a recursive version. We would see how it's working. Only this part is different. You see over here. So if obviously since I'm reducing the size of the array or list whatever every time, so I must have a base condition, and obviously since it is getting reduced, this is what our base condition is. If length is less than equal to 1, then I return the list itself, if length of the list. If it is less than equal to 1 means what? The list has only one element at least. So if the list has only one element, it is that single element itself. So I can just return L or because this means the single element, or I can return L0. But that doesn't matter. L0 and L are same code. Right? So this is my base case, right? Where it would return. Otherwise, if it is not my base case, then how I am doing it? See, now sorted list insert method does what? It inserts second parameter at proper location in first parameter. Right? Sorted list method. Now what does insertion sort rest still does? It is this recursive method that we made. Now sorted list insert method's first parameter is this thing. Right? It is the recursive call of insertion. And second parameter is first of it. Okay. Now let's say we have a list and see the example how it boils down. Okay, let's have a list. Our list is, let's say, suppose, let's take 1, 9, 2, 12, 16. Let's say only 4 elements are. Okay, this is L. First time, obviously, length L is equal to 4, which is not less than equal to 1. So I come over here, sorted list insert. Okay, insertion sort rest of L. We delete this, so that will just this. Fine. Insertion sort rest of it. So what would happen? I'm writing IS, insertion sorting. Okay, so first of all, IS is called under what method? It is called under the procedure sorted list insert. Procedure, sorry, not procedure, sorted list insert. Sorted list insert. Right, this one. Inside that I had what? Insertion sort. And insertion sort is rest of L. What is rest of L? If this is my starting, it should be
9 to 16.
Great. Fine. And it had two parameters, right? What was the second parameter? First of L.
Yes, sir. 1.
Nah, 1. So fine. Okay, great. Now this is my condition. Now if this is the case, remember what we did in our discussion, that whenever you get a function call, right, you would immediately go to execute that function. So since I got here insertion sort function call, I would directly go inside the body of this function. So now let's see what it happens. So insertion sort, again I go, this is the same function. Now the list size is small. Initially I had insertion sort on 1, 9, 2, 16, and now the list size is 9, 1, 16. So again it is not less than equal to 1 because my current size is 3. So I come over here, right? Sorted list insert. So again, sorted list insert. Right? Inside sorted list insert, again I would have again one insertion sort. And now this time the list is what?
2, 16.
2 and 16.
First element is 9.
And my first is 9. Okay. Fine. Again same concept. There is a function call, so go directly. Okay, again size is 2, which is not equal to 1 or less than 1. So same thing again happens, sorted list insert. Okay, insertion sort. 16 is the only element now, and 2 is the other element. Now when I again go to the call for this method, now this is a single element, right?
Yes.
Now this is the base case that is executed and I return them. See what is L at this point? 16 itself, right? So I just return 16. So where would 16 be returned? 16 we return at this point, right? This point. Basically inside SLI.
Yes, sir.
Over here, inside SLI. So 16 is returned. So what is SLI now? So this SLI is nothing but, let me just now write what it boils down to.
16, 2.
Yeah. Thanks. Right. So now 16,2 is a value, then I can solve SLI in 16,2. Right. So we have seen that sorted list insert method, it would work and it would accordingly sort it.
Sir,
So
I have
at this,
yeah. We are returning L. So L is a list of it's not an element 16. I think it's a list 16.
Yes, it's list.
we are returning the list, the whole list. But the thing is, that's what we need, right? Because inside the procedure sorted list, it's not an element, it's a list that we are passing.
Okay, sir.
Okay. Our idea is what? Put X element, X is an element. Put X element
Yeah, listen, list.
inside list L.
Yes, sir.
So okay, so 16 to SLI 16 to is now it materialized to this value, right? In order to get this 16 and 2, I had to go down this whole tree chain of recursion. And now once I reach the base case, now I would return and now my values would start getting materialized. So now SLI 16,2 I have, again simply now I can, since I have this list as 16, okay. So this is actually, sorry. Yeah.
Yes, sir.
Oh, yeah. So 16,2. Okay, so I have this, again this method would work and it would insert the list, and what I would get over here is what? SLI.
2, 16.
Yes, correct. But one important point is now where would the function return after executing this SLI 16,2? See, SLI 16,2 means this line. This line is itself a function call, right? Up to here. This whole thing is a function call corresponding to sorted list insert. But when was this function call made? This function call was made over here, right? So IS made this function call. This IS made this SLI function call.
Yes.
So that's why I must return to this IS. So my sorted list of 2,16 after SLI works would be returned where? Would be returned to
This
IS.
Okay.
Fine. Now, actually, coincidentally, this is already sorted 2,16. But let's say if 16 was ahead, then it was unsorted, then I would get the sorted version at this point. Now, once I get the sorted version of IS, now again what? Once I get this IS result, right? So I can just sort it up again, and then again my material, this would be materialized, right? Because 9 and 2,16 would be the list. So that would again get sorted, and I would get SLI of what? 9. Sorry, not 9. SLI of 2, 16, and 9.
Yes, sir.
Right. Now again same thing, SLI would return on the top function over here, right? 2, 16, and 9. And now obviously again this would happen. Now you can see the change because this list would be actually what? 2,
Yes.
9, and 16.
9, 16. So, comma 1.
So once it again goes to IS, the result will come back to IS, and 1 is there. So again SLI gets materialized as 2, 9, and 16 followed by 1. So finally, once this is executed, our list gets sorted, and obviously our function moves out of, and that's the final bracket, final moving out. So this is where our program terminates with the sorted list of 1 to 9, 16. Fine. So no changes in this method. Only thing is we observe that every iteration of insertion sort, we are having the prefix subpart And then in prefix part, we are inserting one element every time at its proper position. So that is kind of a recursive step, and that's why we did it in this manner. Okay, I hope if you go through this whole tree kind of structure with the value, it should be clear. Or if you know how the sorted insert list insert works, then I think it should be clear. Okay, so now that's it for recursion. Now coming to depth first search. Okay. So depth first search, as I told you that. Okay, by the way, any doubts in recursion?
No, sir.
Okay. Fine. So what is depth
Sir?
first search? Yeah. Yeah.
Sir, but after this, will you take the questions, right? Because the question is related to recursion in practice assignment, which I have doubt. You
Okay,
replied
fine.
on
So
that
ask,
also.
ask. Yeah, ask. Now only yours.
So you replied on that also, the HCF or LCM. Let me check the mail.
Okay, wait. Let me just.
Yes, HCF.
Yeah, practice assignment 11, question 5.
Okay. Question 4, 5. Yeah, this one, right? Yeah.
Yeah, sir.
So this is not clear, right?
Yeah, so you replied to me on that, but
Yeah, yeah. I couldn't discuss the whole thing over their writings. Yeah. Good, you asked. Fine. So let us, in order to do this, wait, I need to have the function side by side. Where is that? Can you all see both the window?
yes,
sir.
sir.
Yes, sir.
Okay, fine. So by the way, so this is the question. Right. So we have to solve same thing. No, nothing difficult. The only thing is again you have to keep in mind that which level do we return at every point. See, so what was our call? Our call was calculate 14 and 17, right? What was it? Yeah, calculate 14 and 17. Right, so this is my first call. Calculate 14 and 17. So now let's just iterate through it and see. So first of all, A is 14 right now, right? So A is less than 14 is less than 17. Is that correct or not? So yeah, that is correct. So since 14 is less than 17, right? So this line would be executed. Return calculate of B comma. So what it is doing is just swapping. So the first thing that's happening over here is calculate of 17 comma 14, right? After that, what's happening? So 17 comma 14 means what? I told you, whenever a recursive call is, whenever a function call happens, not only recursion, a function calls, you directly go to that function, right? Without executing whatever is further there. So I go over here inside this calculate method again, and now I have A as 17 and B as 14. So now A is 17 and B is 14. So this condition is not satisfied. And this is also not satisfied. And now I get difference of A minus B as 17 minus 14, which is 3. Right? So yeah, okay, done. So my next would be difference of difference equal to 17 minus 14, which is 3. Now difference which is 3 is greater than 14 or not. So it's not correct, right? Difference is not greater than 14. So 3 is not greater than 14. That's why I come to the else part. So else part calculate of B, which is 14 and difference is 3. So that is what 14 comma 3. So next call will be 14 comma 3. Okay, again come to the first. Is A less than B? No, A is 14, B is 3. So it's not less than. Now I return, so if A is equal to B, that's also not correct. So again I see a difference. So A minus B, so 14 minus 3 I would do, and that would give me what? 11, right? So again, if 11 is greater than 3, now that is correct.
Yes,
right?
sir,
Into
getting
the-
it now.
yeah. So, let's do that, calculate. Since this is correct, difference is 11 and B is 3. So calculate of difference comma B, that is 11 comma 3. Sorry. Yeah, correct, 11 comma. Okay. So again, go to the start. Difference if A is less than B, no, A is not. A is 11 and B is 3. A is also not equal. Again, the same thing. Difference 11 minus 3 is what? 8, right? 9, 10, 11, yeah, 8. So difference is what? 8. If 8 is greater than 3, yeah, 8 is greater than B, same thing. Calculate difference, which is 8, and B is 3. Fine. Again, go to the start, because again calculate is being called. So I start the same thing happens. 8 minus 3 would be 5, and difference is 5, which is greater than 3, which is correct. Same thing. Right. Again, go and see what happens. 5, same thing again. 5, same thing would happen. 5 minus 3 is 2. Okay, now it would change. So 5 minus 3 is what? 2. So difference is 2, and 2 is not greater than 3. So now the else case would be executed. So now I would calculate 3 comma difference, which is 3 comma 2. Okay. Now start again. If A is less than B, not correct. A equal to B, not correct. Difference 1 is correct. A minus 2, my 3 minus 2 is 1. So my difference is 1, which is not greater than B. So else condition again. So B is 2 and difference is 1. So that's your again one calculate. Right. Again, not equal. Same difference thing happens. So difference of 2 minus 1 is 1. Right. So difference is 1 and greater than B is false, because both of them are 1. Difference is also 1 because A minus B is 2 minus 1, which is 1. So difference is 1 and B is also 1. So both of them are 1. So it's not correct.
Equal.
Yeah. So you get go for else statement. The last time calculate 1 comma 1. So once you go for it, this statement A
Return
equal to B.
B,
That
yes.
would happen and you would return
Thank you,
false.
sir.
Actually. So how many calls happened by the way? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 was the answer, right?
Yes, sir.
Uh,
Must be.
9.
Yeah, 9. Yes.
Check it. Yeah, fine. So, all you need to do is just keep track of. That's why I was saying all questions that would come in your exam would be something like this. At least this was easy because you did not have to jump back, right? Every time we are going forward, and every time you went in one direction, and you just returned at the last level. But some question can come where you have to go down and let's say come back a few steps, again go down, and then again come back a few steps, and then maybe again go down. Something like this can happen in recursive calls, right? So this is where you have to be very careful to which level you are going down. If you are going at this level, keep track of the variables at this level. If you somehow misinterpret with the variance of this level with the variables of this level, then you would get into error. Okay. So yeah, just be careful about that. Fine. Any other doubt?
No, sir. Thank you.
Okay.
So
So
one thing I want to understand that till now in
yeah.
pseudocode we haven't used else if, and in many of the programming languages like Python and so we use. So why is that?
Never used else if?
Not in the pseudocode till now. I didn't see something like
Okay.
similar.
Might be. I don't have any reason for that. Even I didn't know that we never use this. But anyways, yeah. So the thing is, since you mentioned it, let me just state it. So how if else work? If you have for everyone else as well. If else works is if you put some condition, some statement over here would be executed. If that condition is not satisfied, whatever you put inside the else block, that would be executed. If you do not put any else block, then whatever is the next line of code, that would be executed directly. Right after the if block, whether it is executed or not. What happens is, let's say you have multiple conditions, and so what happens in this case? If you have if condition 1, right, and then you write again if condition 2, and then have some task over here, some task over here, and if condition 3, some task over here, and at the end you last write else condition, some task over here. So what would happen is your program would your pseudocode program basically start from here, right? So it will check for correctness of condition 1. If it is true, it would execute this line of code. But the point is, it would also check for condition 2 to be true, even after executing this line of code, right? So if condition 1 means, let's say this condition 1 gets satisfied, so this line would be executed. But again, since in the next line another if is there, again condition 2 would also be checked to be true or not. If it is true, then this line again would be executed. If it is not true, then this line wouldn't be executed, right? And then I would move to if condition 3, and condition 3 would be checked. If it is found true, again this line would be executed. And if it is not found true, then else this line would be executed. You know that the last, the else always matches up with the last if statement. Okay? So this else is corresponding to this if, not these two ifs. Okay. So this is how the general if condition and else condition works. But let's say here the problem was, not problem, here the thing was that all the conditions of ifs were checked, 1, 2, and 3. What I want is if one condition, so it is kind of a unique one. So let's say from among these 3 cases, only one case should be holding, right? So if let's say condition 1 holds, then I should not check condition 2 and condition 3. Okay, something like that. If condition 1 fails, then only I would check condition 2. If it gets satisfied, then it's fine.
Okay, got it, sir.
Right?
So one more thing, like in many of the
Yeah.
example, in when we're solving a pseudocodes.
Yeah, just a second. I have not mentioned that what we have to do in order to get that feature. So for everyone else as well, that if I want to have this thing that if condition 1 gets satisfied, then I don't want to check condition 2 and 3 at all, right? So in those kind of scenario, when you do not
Yeah.
want those condition to be checked, so there we write else if. So you write if condition 1, right? If C1, you have the lines, and then you write else if or elif, right? In some languages it is ELIF elif, but this elif actually is totally the main word is else if, right? Else if. But anyway, in Python you would see that it is elif, but anyways. So elif condition 2, and we can have multiple elifs, elif condition 3, whatever, and then maybe at the last you write else, right? So this else would match up with this elif, and if this if gets satisfied, ellipse would not be checked. If this if fails, then elif would be checked. This first one elif would be checked. If this elif gets satisfied, then C2 would be executed. The work under elif condition C2 would be executed, but elif C3 wouldn't be checked. But if elif C2 fails, then only elif C3 would be checked. If elif C3 also fails, then else would be. Okay, so that's the difference. Yeah, you are asking something.
So one more thing, like when we are solving some of the big pseudocodes, usually when we go by the intuition, sometimes we make error, but whenever we go with the raw data set,
Yeah.
how should we decide that we should balance out that we should go with the always raw data set or with the intuition or the language there?
No, I couldn't get your point actually. Raw data set is the tables or the data set that you're talking about. Fine.
So it's like sample, like you're explaining some of the, like you just explain this calculate function with the recursion.
Okay.
When we take an example, we can automatically clearly iterate over our procedure or our program that we have. But if we sometimes go by just the language of the program and didn't take an example or some raw data to test it out, sometimes we make errors. So how should we decide that we should go with the we should consider some of the boundary cases and test it out first as we iterate our process, or just we have to just group how should we tackle this thing, where we should consider that thing and not?
Yeah, see, so there is no shortcut to this kind of problem. You have to run it and then see where the issue is occurring. Try to figure that out and solve for the corner cases. So that's why I said Recursion actually helps with solving these corner case issues, which would happen in iterative, in programs with loops, you would actually have to deal a lot about these corner cases. So, yeah, there is no other way of it.
Can you also please revisit the topic of DFS that sir explained using the pseudocode?
Yeah, DFS I have not yet started. I came to discuss this. Now I would start DFS. Okay.
Okay, sir.
Fine. So now recursion is done. One example also we saw. Now let us go back to our DFS discussion. Yeah. So what I was saying is DFS is what one kind of, it's a so you have graph traversal algorithms. That means as of now you just consider these as techniques. Okay. Now, what is, by the way, algorithm? Algorithm is any program which should terminate. Very simply speaking, I mean, if you have a line of some lines of code and it is operating on something, doing some meaningful task, and it is terminating in a specific amount of time without any error, then we call such a set of set of lines of code or such a program to be an algorithm. Okay, it's a correct. Basically, this means a correct piece of code which terminates. That's the definition of algorithm. Okay. So graph traversal algorithm, there are multiple possible algorithms and different subcategories among them. But DFS is one such example. Okay. And another prominent counterpart of DFS is BFS. Okay, sir is also mentioning this for some short duration, that this is depth first search. Okay, depth first. And this is breadth first. Okay, depth first search and breadth first search. Now the thing is, let us have a brief graph and discuss that. Okay, no, not graph. Sir has actually one graph. Right? Let us discuss on that one. Yeah. Go to the starting point. Yeah. Suppose we have this graph. Okay, now I start by DFS, right? My depth first search. You know, it is a traversal algorithm. So what we would do is we would just simply walk around the graph, right? We would walk around the graph by a procedure, by following some rules. What is that rules that I would discuss now with this example along the way? So DFS, now obviously since you are traversing on the graph, then you should have a starting point, right? So let's assume that in this example, the starting point I am telling you to be the node 1. Okay, start from node 1. Okay. So now let's see. So how DFS works is, we learned the concept of recursion because we would implement DFS using recursive code. Now the motive of recursion that you have saw that whenever you get a recursive function call, right, you do not execute whatever is after that in the current version of the function. You simply go to the new function call, the new version of the function call, right, as soon as you see the call, right? So here we would do something like that. Just assume that each version of the function call of DFS would be one function or procedure, right? So each version of the DFS call, and we would implement DFS using recursion. That's why I am saying each version. So each version of DFS call corresponds to a specific node on which now you are staying, right, in this graph. Your intention is to traversing the graph, traveling through the graph. So at every point you would be on one of the vertices, right? So assume that every nth iteration of ith, let's say ith iteration of DFS means that you are on some particular ith node. Okay, so that's the idea. And when you go for I plus 1th iteration of DFS, that means you are on the next node. Okay. Now, one important point is, as you know, that recursion works by simply blindheadedly going to the to the start of the function whenever you get an invocation of the function, right? Without worrying about what were the lines of code after my call that you left. Once you complete that call of the recursive call of the function, then you return back to execute those lines of code. So that's why the way in which DFS algorithm works is that uses recursion. It actually goes from one node to the very first node, that is sees, and from that node to again to another node. So let's say if I start my search from one node, right, from here. So I have two possibilities, thus to visit 2 or to visit 3 from 1. And also, sorry, not 2, 3 possibilities. I can also go to node 2. So I have 3 edges, 2, 2, 4 and 3. Okay, but DFS, what it would do is, let us assume that now you have 3 options to choose, but we basically would follow the, let's say, numerical order. I mean, whichever is smaller, we would go to that. Okay, that's not something compulsory for DFS. Okay, but that's what we would follow in implementation. So in your exam, you should follow that. That we would start the DFS. There are 3 possible. I mean, there are 3 possible neighboring nodes of 1, and you can actually, by the theoretical definition of DFS, you can choose any one of them. But in our discussion, in our questions, we would follow the concept of from smaller number to larger number. If you have 2, 4 and 3, then you go to 2 node first. Okay, unless mentioned otherwise, this is the convention we will follow. Okay. Now, so I was at 1 and I would go to 2 because that's the smallest number among my neighbors. So first call would be DFS of 1. Let's now start the writing part. First call would be what? DFS of 1. Not DFS of 1, n is okay. Anyways, as of now, just write DFS of 1. That is on my first node. After that, I told you that we pick DFS of 2, smaller number. Now see, now I could have gone for DFS of 3 because I started from 1. My 3 neighbors were 2, 3 and 4. So I could have done DFS of 1. Then the first neighbor is 2, the second neighbor is 3, and the third neighbor is 4. Let's visit the 3 neighbors at first, corresponding to 1. Right? Since we anyway have to travel through the entire tree, let's do the order of traversal in this manner that whenever I get my neighbors, I would visit all the neighbors in their numerical order. So since at 1 I had 3 neighbors, I could have decided to go to 2, 3 and 4 at first. But that's not DFS. That's not how DFS works. How DFS works is it goes to 2. Now I told you that since we implement this as recursion, and recursion does what? It simply moves to the immediately next iteration as soon as it sees its invocation, right? So and DFS, I told you what does DFS of I means. DFS of I means you are at the ith node. So when I get DFS of 2, that means you are executing corresponding to your second node, and that means the next iteration would be not the neighbor which you left behind for 1, but the neighbor which you would get for 2, because that's how recursion works. You don't worry about which you left behind. You simply go to the function call and execute that, and then at the end of the base case, you return back to the previous lines. Right? So when I get DFS2, I simply go to DFS2 means the neighbors of 2, and I forget about whichever neighbors of 1 were left out. Right? So that I do not consider. So here I would not go for DFS of 3 or DFS of 4. As of now, because 1 corresponding to 1 having 3 and 4, I am not taking DFS of 3, 4. Now I would check what are the neighbors of DFS of 2. Right? So now what are the neighbors of DFS of 2? Now 1 is already visited. One important concept is, as I would discuss again, this visited is here, right? So this visited dictionary would store that which of the nodes you have already visited, because let's say from 1 you have came to 2, right? And somehow later on when you go to 3, you can again go to 1, or even at 2 this edge is there, right? You can say that okay, from 2 to 1 again I can go, but that is meaningless because 1 is already visited. So we keep track of the visited node by using a visited dictionary or whichever one data structure. Here it is a dictionary only, but anyways, you can maintain any possible order. Fine. So the next number would be what? DFS of 2. I would check the neighbors of 2. And neighbors of 2 are what? 1 and 3, because there are edges. This edge is there and this edge is there. Yeah. But obviously 1 I would not take because 1 is visited, so I would go for DFS of 3. Please keep in mind this 3 is because of 2. Not because of 1, it was neighbor of 1.
Yes.
Okay. Fine. So that is done. After that, what happens? So immediately, since DFS happens, what recursion, same logic. As soon as you see recursion, you go to the function call itself. So DFS 3 means the neighbors of 3. Now see, I had 2 neighbors of 3. This one, 2 and 1, but all of them have already been part of my DFS sequence. So
it's again come to DFS of 2.
yeah. So what I would have to do now is, this is kind of my base case that I have I have reached a dead end. I cannot go further. So I would do what? I would return back. So this will be a return back to 2. Because why? Because the DFS 2 version was the one which called DFS 3 version. So I would return back to DFS 2's version. Now I would see that do I have any leftover? So now I would check the leftover. Initially, when I got 3 corresponding, in the version of 2, when I actually got 3, I did not check whether 2 had any other neighbors or not. I directly went for 3. But now, since I'm returning from 3 at 2 again, because 3 has reached a dead end, now I would check whether there are any further neighbors of 2 or not. And I see that 2 had only 2 neighbors, 1 and 3. 1 and 3, both of them are visited. So I do not have any other neighbor. So I would again return back from here to 1.
Yes, sir.
Okay. Now DFS 1 is the, now again I see that, okay, 2 was addressed.
4.
I have, 2 other neighbors, 3 and 4, but 3 is already being addressed over there. So I will go for 4. So now again, this would be a separate path for my DFS traversal, which would be DFS of 4. Why I drew it in a separate branch, where why I did not do it over here? Because it's a separate branch, right? I'm coming back to my parent node and then again traveling along another path. So that's why we wrote DFS of 4. Okay, now same concept. 4 means immediately forget about whether 1 had any other neighbors. Let's see whether 4 has neighbors or not. 4 has 8 and 5, 2 possible cases. We know that we would 5.
Then
Now I would work with fast.
Then 5 will go to 6 first.
6 to 7.
No, 6.
5, where will 5 go?
6.
Just a second.
Then 6 to 7.
5 will go to 6.
Just a second, my pen tab is hanging. Yeah. So DFS of, after that I will go for 6.
6 to 7.
And then
Six.
7.
7.
7.
6 will go to 7, yes.
Again 7.
And then return.
Yeah. So that's why I was thinking. So once you reach 7, right? So what are the neighbors you have? Only 6 and 5. Now both 5 is addressed over here and 6 is the one from which you came to 7. So you cannot go in either direction. What you have to do is, you know that I have reached a dead end. So I must return back. So now you would return back to 6 and check whether there were any other neighbors of 6 that I left out. Okay. So you return back from here to 6. Why 6? Because 6 was the one which called DFS of 6. So you return back to DFS of 6 and now check whether there are any other neighbors, and you see, yeah, we have neighbors 8 and 9.
8.
Right? I will pick the 8 one. Again, separate branch I am doing, because whenever you return, you must create a separate branch.
Then 9.
DFS of 8. I can go from here to DFS of 9.
9 to 10.
And from 9 to 10. Correct. Thanks. So DFS of 10. And that's it. Did we miss any one? No. So DFS of 10. Okay. Now the thing is, this is not where the actually algorithm terminates. What happens is, your result is out, but what internally would happen is, once from DFS of 10 it reaches, right?
Return 9, 9 returns 8, 8 returns.
Correct. Correct. It traces back the path, because once you have reached 10, you do not have any other neighbor. So it's just like all of this returning condition, right? When you have to return here. So now from 10 to 9 it would go back, 9 to 8 it would go back, 8 to 6 it would go back, 5.
5 to 4, 4 to 1.
That's it. And this is where you're finally, this DFS one, I told you those step concept, right? The system step. So initially at the bottom, DFS of 1 would be there. And once you move out from here, right? So this entry would be popped out and your program would terminate.
Yes,
Right?
sir.
So this is how DFS works. Now just I would briefly discuss how BFS would have worked in this case. Right? We would not discuss how BFS is actually implemented and all, because that requires some data structure knowledge. So the second is DFS or the breadth first search. So why do we call it depth first search? The reason is, see, you are just running like, I mean, in the depth, right? So you went like this, then you went like this, you saw a dead end. So after that, you came back to dead end, came back to one, then like this. So basically what I'm saying is you are going in a single path, I mean, in the depth like this. Okay, so that's the problem. So not problem.
I have one question.
Yeah.
So, if we go from 5 to 7 and then 6 to 9 and no 6 to 8 and 8 to 9 and 9 to 10, then we don't have to go back from 7 to 6.
Correct. But we are actually following this methodology of picking up the smaller numbered vertex first, right? That's why we are doing that. Okay.
Oh. Whichever is smaller, we have to go there first.
That's what I said, right? So by the concept theoretical definition of DFS, there is no bound on you that you have to pick up any smaller number, or if you have represented your vertices with alphabets ABCD, then you have to pick the smaller alphabet or anything. There is no bound on that. DFS can travel and by choosing any of the possible neighbors at a particular node.
But in this case, the path will be retraced from 7 to 6, no?
Yeah. That's what I'm saying. DFS does not mention any bound, but here in our course we would deal with this bound, right? Because otherwise there would be multiple possible DFS order of a particular graph between two same nodes. Even if you start from the source node as same, as you can see over here, I did in one order, you can do in another order. There can be someone else who picks up the other order. So there can be multiple possible orders of DFS for a given graph, conceptually. That's why we need to follow some proper rules so that we can frame questions, and that's the reason we would follow that. We would have these nodes represented with numbers, and in your exam you have to pick up the DFS order by following the rules that you pick up always the smaller numbered vertex. Okay, but you are correct. If we would have gone to 5 to 7, we need not have to trace back path and all those things, and still that was also DFS. Once it, I mean, as long as you follow the concept of whenever you call the DFS I, you go to the ith vertex without thinking about whatever neighbor my parent vertex were left out with, right? Just go to the ith vertex. But let's say you hit a dead end at the ith vertex, then you return to your parent vertex, and then you check whichever neighbors other than I have that I left out. So this is the whole philosophy of DFS. Okay, so as long as you follow that, it's still DFS. There are multiple possible orders of DFS, which are correct order for a given graph between the same source and destination. Okay, fine. So now let's briefly see what this graph would have produced if I would have used using BFS. BFS is what? Breadth first search. Now this is not going in the depth, right? I mean, so it would not just run along like this. What it would do is BFS would return the smaller distance located vertices first, right? Yeah. So if I start from 1, so my order of your BFS call would be, the BFS is not mostly implemented with recursion, so I am not writing BFS 1 to BFS 2. I will only write the order in which the BFS statement, I mean, the nodes will be printed. Okay, so let's say I start from 1. So my first node will be 1. Now in DFS we directly move to the next node without thinking about the leftover neighbors. Only one of the neighbors picked up and moved with it. Here we would not do that. Here we would at first take care of all the neighbors at a particular level. Then I would go, and that's why we call it breadth, because this is the breadth of it, right? So I'm considering 2 and 3, both of them together for 1, right? So this is the breadth, right? Considering both. And if I would have directly taken 2 and like this, so that is I'm moving in depth. I mean, I'm moving whatever I can see in front, right? So that's why that is depth, and this is breadth. So at first 1, then what? If I pick, even if I pick alphabetical, by numeric order. So 1, 2, and then 3.
Sir, 4 too, sir, because 4 is one of the breadth.
Yeah, I'm writing 1, 2, 3, and then 4, because all of them are together. But the thing is,
one more thing, sir. So in
Yeah.
this, it's not important whether I am writing 2 first or 3 first or 4 first. I mean, after 1, it's not important, right? Like, it's okay if I am writing 1, 3, 4, and 2, then also it is fine.
Exactly. Again, same concept. So anyway, BFS is not in our syllabus. So theoretically, it's not important. Any of the 3 possible orders are okay. But again, in the courses where you learn BFS, so there we would follow this system of picking up the smaller numbered vertex. Okay. So then you have to pick 1, 2, 3, 4. Okay. Or we would tell you pick up the larger number vertex at first. So 1, 4, 3, 2 will be the answer. Whatever it is given in the problem statement. Okay. See, the thing is, according to the main concept of either BFS or DFS, there is no choosing between multiple neighbors. You can choose any one of them. Okay, but in order to ask question, we cannot have thousands of, not thousand, I mean multiple correct answers. I mean, if you ask the order, then multiple correct answer is okay. But in many questions, we cannot do that, right? So that's why we are following this rule of we would always follow the numerical order in ascending sequence. Fine, while doing graph traversals. So here 3 is because of 1. Okay, so that's very important. In the DFS case, 3 was because of 2. This is 3 is because of 1. Okay, because for 1 I have 2, 3, and 4 as neighbor. That's why these 3 got added because of 1.
Yes, sir.
But in DFS, what happened? DFS my sequence was 1, 2, and then 3.
Is because
Right?
of
So here 3 was because of 2. Okay, so this is the difference. Although you see the order is same 1, 2, 3, 1, 2, 3, but since we are following that numeral order, that's why this is looking like this. But the thing is, actually, this is happening because of the, I mean, this 3, in this case 3 is happening because of 1, but this case 3 is happening because of 2. Now the changes you will be able to see. So 1, 2, 3, 4. After that, what? So I have all the 3 neighbors of 1 distance apart covered, right? These were all 1 distance apart from the starting. Now I would go to neighbors which are 2 distance apart. Or in order to easily find it, neighbors which are your neighbor, I mean neighbor of your neighbors. There they would be obviously 2 distance apart. So now let's see, do I have any neighbor of my neighbor for 2 which are not yet visited? No, because 1 and 3 are there, 1 and 3 are there. And neither for 3, but for 4 I have neighbors.
yes, sir.
Right?
5
So
and
what
8.
are the neighbors? 8 and 5. So I would go for 5 and 8.
Yes, sir.
Okay. 2 neighbors, add the neighbors at first. If this would have been DFS, what I would have done? I would have picked up 4, 5, and then the next neighbor of 5, which is 6.
Yes,
Now see
sir.
the difference over here. Here I got 6, but here I got 8. Okay. So neighbor is 4's neighbor is 5 and 8. So put 5 and 8. Okay. Now what happens is,
So we consider 5. So 5 neighbor is 6 and 7.
yeah. So now I would pick the neighbors of 5, which is because this is the 5. So 5 neighbor would be 6 and 7. So pick 6 and 7. Okay. 8 is already done. So
Then 8 we consider the node 8 neighbor is 6 and
correct.
6 is already visited. So we choose 9.
9 exactly, and then 9 is there.
Yes,
Right.
sir. Then we see 6. So 6 neighbors are already visited, like 5, 7, 8, and 9. So we move to 7. So 7 neighbors are already visited, like 6 and 5. Then we move to 9. So now 9 neighbors are 6 and 10. So 6 is visited, 10 is not visited. So
Correct. Correct.
So
Exactly.
this is fine. Like, if we have a tree, then we can make it. But if we have to do it reverse, like we have given a data like which you wrote, like 1, 2, 3, 4, 5, 8,
Not
6.
possible.
Then how to do
Not
the
possible.
reverse?
There can be multiple possible graphs. So that's not a valid question. So yeah.
Oh, okay. So not even for the depth first, DFS.
Not even for DFS also there can be situation you wouldn't be able to understand where the backtracking is happening. I can consider a backtrack happening at different possible levels, right? So yeah, that also I can have multiple graphs for DFS order also.
Okay.
So these kind of things you would learn in PDS actually. So you can have trees and graphs, and then an order would be given, and then you have to add some constraint and then say that from this order I cannot create a proper unique graph or unique tree. But what is tree we would discuss later. But let's say if I add such constraints in this given order, then I can actually reverse calculate this to a particular single tree or single graph. So yeah, so we would learn about all those nice insights about algorithms and data structure in PDS. Right? Python would be mostly a language-based learning for all of you, where you would actually try coding for the first time. But PDSA would be the more the brainy part, and how you figure out stuff like the office coding kind of things. Right? So it would be also very difficult, but anyways, that's very interesting as well. So exactly, this is actually your introduction. So BFS, DFS would be coming in your week 3 of PDSA course, right? And we would deal in much more detail over there. Fine. So these are done. Now I would go to the code of DFS. Now, once you understand the recursion, now it is very easy. If you understand the recursion concept and if you understand why that DFS order was working, right? Once I get a neighbor, I directly jump to that without thinking of what other neighbors at current level I have missed. I would think about the other neighbors at the current level. Once I return back, I hit a dead end in the child node or the child vertex, and I return back to my parent vertex, and then I see which are the other possible child or neighbors, whatever, right? Child and neighbor are same thing, child nodes or neighbor nodes. So then you see for other possible child nodes or neighbor nodes, what you want to call it, and then you actually again pick one and go like that. So basically that's what we would do. And one more point was that we can end up in loops, right? So here we saw that we had this, we would end up in loop. So for 1 we went to 2, for 2 we went to 3. But let's say when I was checking neighbors for 3, I would also get 1 as one possible neighbor. So I would not take 1 because 1 has already been visited. That's why I need to store the information that which of the nodes are currently visited, so that at every so that for while considering possible neighbors for a particular node, I can take the decision that let's say I have 3 neighbors for a particular node. Okay, and I can see that whether the number which is numerically smallest, right, I would pick that one. But among those 3 numbers, the number which is the numerically smallest number, the node corresponding to that is already visited. Okay, so I must have that information that it is already visited previously. So that information is stored in the visited dictionary. So that's why I am having the visited dictionary over there. Okay, and I told you what was DFS. I wrote it somewhere. Yeah,
Sir, one thing I want to ask. We are starting from I is equal to 1. So I is equal to 1 is always true.
I is equal to 1, whether you are getting it?
Means visited I is equal to 1. Visited I.
Yeah.
When I is 1.
Coming to that, I was just coming to that.
That is visited.
Yeah.
Visited 1 is always true.
No, it would be true once it is I mean, you would get the point. Just bear with me. Just answer this question first. I think I wrote it somewhere. Or did I delete it? I don't know. Okay, so anyways, what I was telling, I told that what is DFS of I means. I wrote at some point DFS of I, right? So what did DFS of, I mean, the graph and visited are already there. I'm not talking that. Just assume that all the parameters and then I have I. What does this mean?
When I is 1.
Yeah, I is 1. No, I is not 1. I is a vertex. I is just a vertex, right? I'm a DFS of. So in our example, we wrote this, right?
When we start the program,
correct.
DFS of 1 will be true.
Yeah. So 1, 2, 3 are these are what? These are vertices, right?
No vertices. No for this. Because if we visit 1 again from 3.
Yeah, go ahead.
When we start from 1 to 2, 2 to 3, and 3 to 2 and 2 to 1 again, at that time visited 1 will be true or it
true.
will.
It would be true. Why it would be true is, see, I would just draw that. So first let's discuss this. DFS of I means I am currently not I mean the function is currently at I. Is right currently at I vertex.
Yes.
So that means what? If it is currently at I vertex, that means I have already visited I vertex. I mean, now I am visiting, not already. I am visiting I vertex because I am currently at I vertex, right? So since this function DFS of I means I am now at I vertex. So
Hmm.
first thing that I need to do is I would set the visited of I to be true, because now I am visiting.
Okay.
So now I am setting visited to be true, so that in future recursive call, if someone needs to check whether I is already visited or not, they can get the information,
Hmm.
right? So that's why I am now setting visited of I equal to at this version of the recursion, at this call of the recursion.
Okay.
Okay, so that's what I am doing. So initially, if I in our example of the graph, DFS of 1, I would be 1 at first, right? So I started from the 1 vertex. So I would write visited of 1 equal to 2.
Yes.
And some point up, I would discuss this code, but let's say this is the recursion happening, right? So some point with this recursion would happen, and I would get I to be 3 or 2, anything, right? Let's say 3. So when I get I to be 3, and I would check for the neighbors of my, 3, right?
Yeah.
So at that point, first of all, I have visited 3. So that's why I would set this 3 to be visited of 3 to be true. That's my first task, because that's where I am visiting 3 for the first time. So that is done with this line. And later I would see what this line is doing for each j columns of graph. That is, I am checking for all the possible neighbors in the graph where is key visited j. I would discuss this. Is key visited of j is not, not true. We have not visited. Okay.
Yes.
So since this j is what? J is variable of this loop, and now I am for the iteration of third vertex. So this j would exist for the third vertex. This j would actually range from 1 to 10, right? Sorry, how many vertices were there? 10, right? 10. So 1 to 10. So this would range from 1 to 10.
Yes.
So for is visited, when I pass this j over here, and when j is equal to 1, right? When j would be 1, then this j would be 1. So visited of 1 would be checked. Is key is a method just to check whether visited of this j is true or not. So visited of 1 would be checked. You remember that initially when we visited 1 for the first call, we made visited of 1 to be 2. Right? So when this line would be executed in the version of node 3, when this j is equal to 1, visited of 1 would return true, and here I am complementing it with not. So this would become false, and the false is always false. So if condition violates.
Yes.
Right? So you would not actually go to visited with the, this j equal to 1. Corresponding to the version of 3 would not be executed.
We will not go there.
Right?
But visited of 2 will also be true, no?
Correct. Visited 2 will also be true, and that's why visited of 2 would also not happen.
So from 3 it will go straight to 4.
Exactly. So what would happen in that case?
So we don't retrace the path from 3 to 2 and 2 to 1.
Yeah, we would retrace the path and see how that retracing is happening. So let's take the example of 3 only, right? As of now, I have visited 1, I have visited 2.
Yes.
Okay. So now I have visited 3. This is my third. So I is 3. Okay. Now I is 3. So I said visited of 3 equal to 2. Step 1. J 1, 2, 3, like that it would happen.
Yes.
And graph of I is equal to 1 means simply it checks whether there is an edge between the I and j node. I is your 3, right? So the j would follow from 1 to 10. So 3, 1, whether there is an edge or not. 3, 2, there is an edge or not. 3, 3, there is an edge or not. Like that it would go. Okay. So anyway, so graph I, is equal to 1 means it's simply checking whether there exists an edge or not. If there exists an edge, whether that neighbor or whether that vertex is visited or not. So that is in this line. Now see, what would happen is, let's say when j is 1. When j is 1, graph ij equal to 1 would be true. Why? Because obviously there was an edge between 3 and 1. Correct? 1, 3 would be true. Sorry, 3, 1. I is 3. So 3, 1 would return equal to 1 because there is an edge between 3 and 1. But this would return false.
This will be false.
Yeah, visited of 1 was true, and that's why this not would make it false. Okay, so once this is false, this line would be skipped.
Yes.
Right? If this line is skipped, I would move out of if statement and I would move to the, over here in the next for statement, right? Next iteration of for. I would go. right? Now j would become what? 2. Correct. So if j becomes 2, then this is 2, 3 comma 2. Obviously, again I have an edge that is again correct, but again I have visited 2, right? Because before, correct. So again this statement would be false, if statement would be false, and this would be skipped. Now again I would go to outside iteration.
3.
Now see what happens.
True.
J would be 3. Graph of 3 comma 3 wouldn't be 1 because 3 is it's the same vertex and we do not have cell loops. So 3 comma 3 equal to 1 would be false. Right? Okay. So 3 comma 3 is false. Next time once this is false, again same thing happen, it goes to the top. 4. 4, there is no edge between 4 and 3.
There is no path between 3 and 4.
No path, right? No edge between 3 and 4. So obviously, so likewise, we know that none of the vertices over here has any edge.
Yes, none of the vertices will have.
That means for the 1 and 2 vertices, this condition was creating the false scenario. For all other vertices, this condition would create your false scenario.
Yes.
And once this condition is creating false scenario, what does it mean? Then what you do is, for the 10th first, when your j is 10, then you check whether it is false or not. You see it is false, and then you move out, right? You move out from the for loop also. So from this for loop, you go and see that, okay, I have exhausted till 10. So my for loop is also now ended. So after that, what happens? So now for loop is done. Okay, so here you come outside the for loop. Okay, outside the for loop, you simply see a return statement.
Yes.
Now, which return is it? That's what I told, right? DFS of 1, DFS of 2, DFS of 3 was the sequence in which I called. And after DFS of 3, I couldn't find anything because my for loop ended.
Yes.
Right?
Yes.
And this was my DFS of 3 version, which is this version. Correct?
Yes.
And from there I returned. Where I would return, just recapitulate the regression concept, we would return to the point where the current version was being called. DFS 3 is the current version, and that current version was being called inside DFS 2, right? So in this line, this is where I am calling DFS. The recursion is happening in this line. So inside the DFS 2's method body, I called DFS 3. So that means when this I was 2, right? When j became 3, I made this 2 comma 3 case equal to true, and obviously 3 was false. I did not visit 3 at that point of time because I am talking about this point of time when I was at 2. So this is the 2th version, right? So visited of this is false and not of false is true. So that means this line was executed inside the version of 2, and that is where I was calling the version corresponding to DFS of 3. Right? So when DFS of 3 is returning from here, where it would return? It would return here, where it was being called, inside the 2's body, version of 2. So once I return over here, right, this is executed. So I would do the next task after this. Okay, so now it is 2's version. So what is the next task after DFS of 3? There is nothing. We are closing the loop. I mean, at the if statement, not the loop, the if statement.
Yes.
Right? So again, I would go to the loop and check that whether there are any leftover neighbors of 2 that I have not visited. 3 I have visited, but 2 I have not visited. But other neighbors of 2 I have not checked. As soon as I got 3 over here, I moved to 3. Now I returned from 3 over here, right? And now I see that, okay, since my work is done, I have to now check for any other possible neighbors for 2. And now I see again the for loop iterates. From 3 it becomes 4, and again you would see with 2 none of them would have any connections. 2 was also separate, right? So again the graph I comma j equal to 1, this would be false for 4, 5, 6, 7, 8,
Yes.
9, 10. Same steps
None of
repeat.
them is 1. None of
Correct.
them.
Correct. So once my 10 for each it exhausts the 10th condition, it comes back out of the loop and see if there is again a return. This return would be happening for which one? DFS of 2.
Then you have to go back to 1.
Exactly. So now where it would go back again, like 3, when it returned from 3, right? It went to the corresponding version of 2. Now it is returning from 2, right?
To
Now
1.
it is return to the corresponding version of 1. So when this was 1. So now you see where the retrace is happening. This is the retrace. When you move from 3, you came over here where the version was 2. This is where you are retracing back from this node from 3 to retrace back to 2. And then again, when you exhaust all the nodes of for loop of 1 to 10 for 2, then again you return to the version of 1, that is this retrace.
Yes, now one will check with 4 instead
Correct.
of 2 and 3, because 2 and 3 visited will be true.
Exactly. Now it would check with 4 in the for loop and it would get a match in both cases. It would be visited would be false for 4. So not of false would be true and graph ij would be 1 because it has a h. So again it would call DFS on 2 and likewise it proceeds.
Yes.
Done?
Okay.
That's it.
Thank you, sir.
Yeah.
Sir, cannot we just avoid the return statement, return visited, because visited itself is a dictionary?
See, here, whenever we are calling DFS, right? DFS, right? We are storing it inside visit. That's why it is so. But you can have implementation where you may not return it, provided that you. Anyways, we are passing the visited itself as parameter. Yeah, so maybe it's not required. Yeah, you can remove the return. Because every time you need the changes made in the visited, you are passing it as parameter, so it's there. So you can remove this line and remove this visited, just directly write DFS. That also works, right? But you must keep this parameter, otherwise you will not get the latest version of visited. Yeah,
Okay.
correct. Fine. So that was it about the main discussion, the 4 concepts. And whatever sir is discussing, there are 4 parts about applications of the DFS. How we are discussing some case studies. Go through the lecture, see how applications of DFS work. Okay. And yeah, if any doubt is there, you can ask.
Sir, recursion concept is not that much intuitive for a starter. So can you just give a few more examples where we can apply this beside this summing and beside this DFS? DFS was a bit complex, but we got it. A few more examples will be a good deal too.
Okay, so see, as I said that most of the recursive code are doable in iterative manner and vice versa. So, but if you really want the usefulness of recursion, right? I can give you 2 possible scenarios. The first would be not give 2 possible. I can tell you 2 possible scenarios. The first one would be some basic example where you can use recursion. But that would be you can use recursion. You can use or you may not use. That's upon you. But you would not get the crux of recursion or the usefulness of recursion idea from those examples. The second thing is second kind of examples would be one where you would actually understand, okay, this was very much difficult, right? And if we do it using loops, it is very difficult. If you do it using recursion, it's super easy. So that second kind of example, I can only tell you, but I cannot discuss because if you are interested, you can check online or on some book, in some books. So those examples would be proper algorithms. Like if you let's say do dynamic programming, then you would see there is a concept of memoization and DP. So I mean I don't know. So we have to. I would say you have to wait for that. Maybe, but in order to get the exact use of recursion, how it is easy to understand. Now you are feeling that recursion is difficult to understand. That is okay. It is a bit difficult to see how we can write the recursive code. But once you write the recursive code, it is easy to understand, right? So, but if you do a very difficult problem solving using iterative code, it becomes much more complex to see think about the code, write the code, and work on it. Recursion makes it much more simpler. So that crux of recursion, where it is helpful, that I cannot give you sadly. I can only tell you if you are interested, you can check. You can check dynamic programming concept of memoization and DP. Check what are the differences between them and how it works. There are problems like matrix multiplication. There can be multiple coin change problems. All those things are there. But these are mainly in the programming domain. Not only programming, the algorithm domain. So yeah, so that's where you would get the usefulness of DP. And if you want to just get some normal examples where you can use, I don't know whether you would feel that much satisfaction with DP. Those kind of examples are similar kind of things. This factorial, some kind of addition where you have to do some small task and then inductively build upon the like list insertion maybe one, list summation is one. These kind of examples only which you saw. I mean, I'm not able to give you some very useful or insightful examples for the useful to display the usefulness of things. You have to do that, wait for it in previous. Okay, so just understand the concept. This is how it works, right? Recursion is not that much in most of the courses. Before PDSA, whatever course you would do, recursion would not be that much hard to work with. Okay, in Python also it wouldn't be that much difficult. But recursion would be very required in the PDSA course, and actually there you would also see why it is important. The question that you are asking, it would be answered over there. Right? So yeah, you have to wait. That's what I was saying. Yeah.
Okay.
Sure. Fine. Any other questions? Great. Okay.
So this session was really helpful. Thank you
Thanks a
very
lot.
much.
Thank you. Thank you all. And okay, your exams are on 11th, right? Enter.
Yes,
Yes, sir.
11th.
December 11th.
Most probably I would take one more or two more session, one more session most probably before that. So anyways, all the best to all of you. Prepare nicely. Right?
Thank you, sir.
So
Thank you, sir.
when this two result is
Thank you. sir.
Sorry. Yeah, thanks.
this
Thank you,
two-
sir.
I didn't hear you. Can you repeat?
Thank you, sir.
Thank you, sir.
Yeah. Thanks.
Yes, sir. Sir. Sir, are you here?